Thank you. Hello and welcome to my lab. Are you ready to learn? Yeah. Are you ready to have some fun? Yeah. Well, let's get started then. That was neat, yes, I agree. That was a chemical reaction between a common substance, rust, iron oxide, and aluminum. And I want to tell you some more about this, but first I want to point out to you that in my lab, whenever we do experiments, we always obey the safety rules, and that's why I put my goggles on. And that's why we also have a fire extinguisher ready to be used just in case something goes out of control. We're not planning on anything going out of control. We'll just have it ready to be used, and I'll set it aside here so I can get to it if I want to. This chemical reaction that we just saw is a highly exothermic reaction. It's a combination between two different substances that were placed in the flower pots. I'm going to show you what these substances are. It's a mixture of iron oxide, rust, and aluminum. And this mixture, when it is heated up, it gives off a lot of energy in the form of light and in the form of heat. And what I used is a sparkler, not the common ordinary sparkler that you and I use when we have celebrations. This one is actually made of iron oxide and aluminum. And the high energy that's released when this is ignited is what set off that reaction that we had in the box. That reaction released a lot of energy, and you saw that. Would you like to see it again? Yeah. Well, I'd like you right now to watch the monitor as we show a replay of it. You won't hear any sound. There it is. There it is. And pretty soon, molten iron comes running down the bottom. It's so bright, it's not red hot, it's white hot. In fact, I'm going to show you what's left right now. What's left right now is some hot iron. There it is. That came from the reaction of aluminum with iron oxide. And this reaction is so highly exothermic, it had a very important practical application about 100 years or so, 150 years ago or so. It was used to weld the railroads when the movement to the western side of the country was taking place. I like doing experiments with balloons. I need some more balloons. Can someone please bring me some balloons? Oh, yes, here we are. There. Hello, Akornefa.
Hello.
Good to see you again.
Nice to see you.
Please put them down here. I'd like you to meet Akornefa Achea. She's a student. Where do you go to school?
I go to school at Verona Area High School.
And what year are you in?
I'm a junior.
She's a junior. Yeah. And she's been doing some experiments in my lab, and that's why she's helping me with those balloons. So I'm going to start out with this first balloon here. Okay. I'm going to set it up here. All right. And this balloon has in it a gas. And we're going to find out what this gas is, if it burns or doesn't burn. So I'm going to go like this. You ready for this?
Yes.
All right. Here we go.
Ooh.
That balloon had in it the gas methane, natural gas. The same gas that we're burning in this burner right here. And that methane gas is also lighter than air. But the balloon didn't go up in the air because we had it tied up with this little clamp. So that's why it didn't go up. So we've got some more balloons here. So methane is the simplest hydrocarbon. And it burns and gives off light energy and heat energy. This balloon has in it ethane. Ethane is closely related to methane. And let's see if ethane will do the same thing as methane. Okay, you ready for this?
Yes.
Okay,
ready.
She's ready. Here we go.
Ooh.
Similar, but not exactly the same, right? Release of energy in the form of light and also a little bit in the form of sound. So we've done methane, ethane. What comes after that?
Propane.
Propane. Do we have a propane-filled balloon here?
Yes, we do.
This one here?
Yes.
Would you like to do it?
Sure.
All right. All right, then I'll stand over here then as you do it.
Okay.
Okay, here we go. Wow! That flame went out with that one. That is because of an interesting property of propane, but we'll talk about that in a second. So we have one more balloon. Shall I try this one?
Yeah.
Okay, I'll try this one. Okay, let's try this one and see what happens. Okay, here we go. Ready? That looks, actually, it sounded like it was a dud, right? Actually, it wasn't, because the gas inside the balloon was carbon dioxide. And carbon dioxide does not burn. The other gases that we used, methane, ethane, and propane, when they burn, they produce carbon dioxide, among other things. They produce water and carbon dioxide. And carbon dioxide is a gas that is heavier than air. It's denser than air, so it sinks. Are you ready to do your next experiment that you have developed here?
Yes, I'm ready.
Okay, what do you have for us here?
This contains carbon dioxide.
This flask has carbon dioxide in it. It also has a little bit of dry ice at the bottom, which is where the carbon dioxide gas is coming from. And what are you going to do?
I'm going to pour it down these stairs.
These down the steps here, these stairs here with the candles on them, right?
Yeah.
Okay. She's pouring down a gas, and what's the gas doing? It's putting out the flame, right? That's because carbon dioxide is not only denser than air, but it also, what? Doesn't support combustion. Why don't you leave those for me? I'd like to leave those. Can you leave those for me like that?
Sure.
I want to do another experiment. Was that good? Yeah. So carbon dioxide gas is heavier than air. You saw her pour it down, and it put out the flame. Now, propane gas is also heavier than air. But remember what happened with the propane-filled balloon when we put the flame to it, right?
Yeah.
I have a small cylinder of propane gas right here. I'm going to open the valve and fill this beaker with propane gas. We won't be able to see it because it is colorless. All these gases that we have worked with so far are colorless. So here we go. Can you hear the sound of the gas flowing out?
Yeah.
And we can't see it though. And I want to fill it. I'm going to fill it like this. Now I'm going to close this off. And propane gas is like carbon dioxide, denser than air. But propane gas, unlike carbon dioxide, does what? It burns. So I'm going to pour it down and see what happens. You saw that, right? And actually, that was a lot of fun. I'd like to do that one more time. Would that be all right? And let me fill it again. All right, with the lights down, please.
Ooh.
Akornefa, I know you have other hobbies beyond what you do in my lab. What other hobbies do you have?
Well, I like to play the flute, and I like to play the piano, and dance, and sing, and draw.
Sounds like a typical teenager, right? Right. Did you bring a flute with you by any chance today?
I did.
Would you like to play something for us?
Would you like me to?
Yes, we would love to do it.
Sure.
Yes. That was very, very nice. What was the name of that
Thank you.
piece?
It's called Tambourine.
It sounded very lively.
Very
Didn't we all
lively.
enjoy that? Yes. I want you to know that Akornefa has already played with the Madison Symphony Orchestra. Isn't that something? Yes, yes. And you know something? All of you in the audience, especially the young people, if you think about the talents that you have in music or in science or in anything else, if you develop that talent and if you listen to your parents and to your teachers and to others in their community, you can do whatever you want to do, just like she did. So give her another hand for her accomplishment. Thank you very much. Thank you. Now, when something burns that has carbon in it, it releases carbon dioxide gas. And carbon dioxide gas is invisible. It has no color, so we can't see it. It also has no smell, so we can't smell it. I'm going to do now a set of experiments with a different form of carbon dioxide, not the gaseous form, but the solid form, the one we call dry ice. Dry ice is solid carbon dioxide, and its temperature is minus 78 degrees Celsius. You know, in science, we keep track of the temperature in degrees Celsius, not in degrees Fahrenheit. And everybody in the audience should be able to change from degrees Fahrenheit to degrees Celsius. And if you don't know how to do it, you can ask your parents to help you, right? Yes, look it up in the dictionary, look it up in the encyclopedia. Carbon dioxide in the solid form is at minus 78 degrees Celsius. I use these gloves to protect my hands from frostbite. If it comes in contact with the skin, it'll give me a severe burn, and that would not be good for me or anyone else. And carbon dioxide changes from being a solid to a gas directly without melting by a process we call sublimation. Can you say sublimation? Sublimation. Sublimation is happening right now, but we can't see it. How come we can't see it? Because carbon dioxide gas is invisible. It's colorless. By the way, if you ever see a colored gas, you run away from it, because all colored gases are poisonous. You heard me. All colored gases are poisonous. The converse is not true. There are some colorless gases that are deadly poisonous, like carbon monoxide, which is closely related to carbon dioxide. But carbon monoxide is deadly poisonous. We want to try always to avoid it. So carbon dioxide is coming out of the solid now. We can't see it because it is colorless. I want you to focus your attention on what I have right in front of me here. What shape of vessels do you see I have in front? There's cylinders, right? How many cylinders are there? And they have in them liquids. How do we know they're liquids? We shake them up. We know from experience what liquids do, right, when we shake them up. So I'm going to take chunks of dry ice and drop them into the cylinders. I'm going to do this in a special way. When we get done, you tell me what that special way is, okay? So here we go. Am I putting a dry ice in every cylinder? No. I'm putting a dry ice in every... We make observations. We try to make sense out of these observations. Now, what do you see? Do you see bubbles? Yeah. What kind of bubbles are those? They're carbon dioxide bubbles coming from the sublimation of the dry ice. Sublimation is happening right here outside the cylinder as well as inside the cylinder. We see the carbon dioxide bubbles here because gas is mixing with the liquid. Here, gas is mixing with air, right? And so we don't see it. And we also see a variety of beautiful color changes, right? You see that? That's because we put some dyes in there, and these dyes are sensitive to changes in the pH of the solution, the acidity of the solution, or the basicity of the solution. So the colors that you see of these dyes in the cylinders where I put the dry ice are the colors under acidic conditions, because carbon dioxide, when it dissolves in water, it gives us carbonic acid. And the carbonic acid reacted with whatever was in there so that we can see the beautiful color changes that we're looking at. So in this pair, the color changed from what to what? Blue to, and in this pair, pink to what? Clear is not a color. Look, this is a clear and colored liquid. This is a clear and Colorless liquid, right? Nobody in my lab ever confuses those two words, and none of you are going to confuse them from now on, right? Clear and colorless do not mean the same thing. You see something coming off the top of these cylinders here? What does it look like? It looks like smoke, but it's not really smoke. What it is condensed water vapor. The water vapor is condensing on the carbon dioxide gas that's coming from the sublimation and forming a mist, forming a fog. And what's what it is? The fog, notice, is moving downward. That's because carbon dioxide gas is heavier or denser than air. At this time, I would like you to welcome a very distinguished colleague of mine from the Department of Physics at the University of Wisconsin in Madison, Professor Clint Spratt. Clint? So, welcome to my lab, Clint. Good to see you. How did you get here, Clint?
My pleasure. Well, I came in on the rocket-powered tricycle.
A rocket-powered tricycle. Powered by what?
Powered by carbon dioxide. Actually, I get about 100 gallons to a mile on this thing.
Oh, my goodness. That's very efficient.
But you know, it doesn't use gasoline. It uses liquid carbon dioxide.
That's what's inside this tank here?
That's what they tell me, but I've never seen it because every time I press on this, it comes out as a gas.
Well, that's one of the properties of carbon dioxide. When it's compressed, it's a liquid, and when it comes out to the open atmosphere, it's a gas.
You know, I knew you'd know all about that. That's an important principle of chemistry, isn't it?
It sure is.
But you know, there's a principle of physics here, too, because as that carbon dioxide goes out that way, that pushes this in the other direction by Newton's third law of motion.
And that's how the tricycle got out here?
That's right.
A movement in one direction and?
An opposite reaction.
An opposite
Action
reaction.
and reaction.
Wow.
An important principle. I can
Very.
demonstrate it to you if you
can?
like.
Yes.
Yeah. Let me use this rotating platform over here.
Please do.
I'm going to just step up on this platform with this carbon dioxide, and I'm going to let the carbon dioxide gas come out and see what happens. Well, that's pretty neat, except how do I stop? Oh, the other way? Well, let's try that. Well, you're right. And that's the principle of the rocket. When the carbon dioxide goes one way, the rocket goes the other way. And that's how we travel to distant places in the solar system. Now, you've probably all seen an ice skater go out on the ice rink and start spinning around and then bring her arms in and spin really fast. I can do that on this rotating platform. We don't even need the ice. And I don't even need to know how to stand up on skates. So if I go around with my arms out like this, I'm going not too fast, right? But if I bring my arms in, I go faster. Slow, fast, slow, fast. And that's the principle of the conservation of angular momentum. Lots of big words, but I can make it even more dramatic with these weights in my arms. So let's try it that way. I'll start going around with the weights out at arm's length. I'm not going very fast now. When I bring them in, I go very fast. As you see. And one can easily get dizzy that way. Now, I have here another gadget I bet many of you have at home. Do you have one of these? Yeah. That's right. It's a bicycle wheel. And if you ride a bicycle, you have one. But this was an extra heavy bicycle wheel. I wonder what would happen if I'd stand up on the rotating platform with the bicycle wheel in my hand. Let's try that. Well, not very much. But Bassam, if you'd give this a nice spin.
A nice spin.
Yeah. Oh, that's great. Still nothing's happening. But let's try turning it up like this. Oh, that's pretty neat. Now let's try the other way. Look at that. I can make myself go either way. And that's because of the same principle, the conservation of angular momentum. Or we can also think about it in terms of Newton's third law of motion. When the bicycle wheel goes one way, it forces me to go the other way, just like the rocket. And so there's many important ideas of physics that allow us to understand the way in which things move and many other things that go on in the world around us. You know, Bassam, I have another gift for you.
Oh my goodness, you have just brought lots of gifts right now.
I have, but I want to present you an autographed copy of my new book, Physics Demonstrations.
Oh
and you
my.
know it's inspired after your chemical demonstrations books.
That's very kind of you, Clint. I really appreciate it. It is autographed. Thank you very much. I appreciate that. And I know there are lots of good experiments here that people can use and enjoy. And everyone knows, of course, Professor Clint Spratt for his great program, The Wonders of Physics. If you haven't seen it, you should see it in February. Every year he puts on a tremendous presentation for the public called The Wonders of Physics. Thank you very much, Clint. I really appreciate it. Thanks very much. Thank you. The next experiment we're going to do is going to involve a long glass tube. And to help with this experiment, I'd like to call on our expert demonstrator, Mr. Jim Maynard. Jim? It's a long glass tube. It's got some liquid on the inside. I can see that. Also has two stoppers at the bottom and one at the top. I'm going to strike a match and get up on this stepping stool right here. And in the dark, I'm going to drop the match in. Was that fast? Thank you, Jim. You notice the tube now has a yellow solid on the inside. That's the product of this chemical reaction between something called nitric oxide and carbon disulfide, ignited by the match and released a lot of energy in the form of heat, in the form of light, and also in the form. Let's take a look at it in slow motion and see if we can learn from it. You won't hear any sound, but you'll see the match drop, and there it is, coming very close to the top, and there, Jim and I are trying to get out of the way. We always practice safety in my lab. Well, I want to thank you for coming to join us on this very special occasion, and I want you to remember to do experiments safely, but also to remember, no matter what, science is fun. Thank you very much, everybody. Thank you. Thank you.
Do you want to learn about some fun and informative science experiments you can do at home? Check out the Science is Fun website at this address, scifun.org. You'll discover fascinating facts about chemicals and other great science information.